Hello, everyone. I am Landon. I will be leading this review for, oops, that was drawn horribly. Math 127. All right, so just so you know, this will be recorded and this will be up on the Math Center YouTube page within a few hours from now. And yeah, if you have any questions, suggestions for problems or anything like that, feel free to just shout them out loud, or you can send them to me in the chat. You can either privately message me or just in the chat for everyone to see. Either is fine. And yeah, so that's about it. So let's get started. Again, if you have any problems or yeah, any problems or exercises you'd like to go over, do let me know. I was not given a review, no problems or anything like that. Do you happen to have anything like that?
No, I only have like homeworks,
Oh,
but
I
no
think there may
review.
be an issue here. I don't think I can hear you. Okay. Sorry, would you mind repeating yourself?
Yeah, I said I only have like homeworks. We had 4 homeworks, but that was it. There was no like review packet or anything like that.
Okay, yeah, for sure. Okay, so I have the book in front of me. It's not the most updated version, sadly. It's the 10th edition rather than the 11th. So we could go through some of those problems from chapter 8, which I believe is what's covered during your exam. It's problems like solving for triangles, trying to determine if some triangle has if it'll give you 0, 1, or even 2 triangles, and some other trigonometric type things. Does that sound right?
Yes, that sounds right.
Okay, sweet. All right, so yeah, perhaps we'll just do a couple of problems I have here. I think the first problems they start off with in this chapter are trying to compute the 6 trigonometric functions given a triangle. Would you like to start with that?
Yeah, sure.
Okay, sounds good. All right, so yeah, here's one problem. They have a triangle. Oops, let me draw a bit better. Sorry, this is a new tablet I'm working with, so I'm trying to get used to it. So we're given a right triangle, and we have an angle theta, and we have a 3 and a 4 right there. Okay, and they want us to find okay, yeah, so they want us to find the values of all trig functions. Okay, so that would be sine of theta, cosine theta, and then we have tangent, and then the other ones would be what cosecant, oops, and then they have secant of theta, and then finally cotangent, right? Okay, so they want us to find each of these values. Okay, so sine is, you can kind of think of it, it's like a ratio of 2 sides. Do you happen to remember what those 2 sides are?
Yes, just give me a minute.
Yeah, of course.
They are opposite over hypotenuse.
Yeah, exactly. Yeah, it's opposite over, oh, whoops. I don't know why I wrote adjacent. And then, yeah, similarly, cosine is
Adjacent over hypotenuse.
perfect. And then, yeah, tangent is just the ratio of the 2, which is just
opposite over adjacent. Yeah.
Yep. Yeah, exactly. And then the other ones are just ratios. This is a multiplicative ratio. In other words, just 1 over sine. So you just flip it. But anyway, so we can start with these. All right, so if we want to find sine opposite over hypotenuse, what do you think we should do?
We need to do a squared plus b squared equals c squared.
Yeah, exactly. We need to find the length of the hypotenuse, and we do that by the Pythagorean theorem, exactly as you said. A squared plus b squared equals c squared. And so in this case, we can just kind of arbitrarily assign a and b. I'll say this one is a, and this one is b. and then we want to solve for C. Okay, so we just plug it in. Whoops, I think my tablet messed up. Whoops, why is it being like that? Whoa. Okay, that's sorry, my tablet's being a bit strange. I'm trying to
It's okay.
draw and it's not wanting to draw. It's strange. It's like one portion of the tablet's being weird. Anyway, so yeah, we just plug in 3 squared, 4 squared, and that should be C squared. So we don't want C squared, we want C, right? So we can just square root both sides. So how about we do that? Whoops, again, my tablet's being weird in this area. Yeah, strange. Okay, maybe I should write elsewhere. C equals the square root of 3 squared plus 4 squared. This right here on the inside should be, what is that, 9 plus 16?
Mm-hmm.
I think that's what, 25?
Yes.
Thankfully for us, that's a perfect square. That's 5 squared. So then 5 squared, take the square root, these cancel, and we're just left with 5. So yeah, something you may want to pay attention to is sometimes when we do the square root of both sides, we end up having to do plus minus.
Mm-hmm.
But in this case, we actually don't need the minus. We can just kind of scratch it out. And that's because we're working with lengths. So we just assume that they're positive. So we're kind of making an assumption. But if we want to find all possible values of C that would satisfy this, we would also have to put a minus there. But we're not looking for all possible values. We're just looking for possible lengths. And lengths are always positive, right? So there we are. That's all we need. Okay, so now that we know that, we now need to compute sine, cosine, and all the other values. And that's basically everything we need to set up for this. We have the opposite, the hypotenuse, the adjacent, and everything else we need. Okay, so now we just plug it in. Sine theta equals opposite over hypotenuse. So from this angle, the opposite is going to be 4. Hypotenuse is going to be 5, as we just found out. And then cosine is going to be the adjacent, so that's 3 over 5. Tangent is going to be the opposite over adjacent. So opposite over adjacent, that's 4 over 3. And now we do the other more exotic trig functions. So then cosecant, that's just going to be the reciprocal of sine. So that's going to be, we can actually just flip it, 5 over 4. And similarly, we flip this one, 5 over 3. Finally, cotangent, we do the same exact thing, just flip it, 3 over 4. Okay. Any questions on that?
No.
Okay, sweet. So yeah, some things to maybe keep in mind when going about this, so you can double check your work. Sine and cosine are always going to be less than or equal, well, rather I should say, sine of theta and also cosine of theta. They're always going to be between -1 and +1. So you can kind of imagine just taking the absolute value of them. It's always going to give you something between 0 and 1. So if you get anything that is greater than 1 or less than -1, then you know that there's an issue. And we can see that these are both less than 1, so we're good. That does not hold with tangent. Tangent is a little more weird, but we can apply this logic here to these ones, since sine of theta, or perhaps cosecant of theta is equal to 1 over sine of theta. And we know sine is always less than 1. Well, I have to be careful with my words. I'm implying that the absolute value of sine is always less than 1, but greater than 0. So sorry, when I say that, I'm not being very proper with my wording, but that's kind of what I'm referring to. Its magnitude or absolute value of it is always less than 1. Since this is always less than 1, we can see that cosecant is always going to be greater than or equal to 1. And same with secant. So that's something you can kind of keep in mind and try to double check that they're good. We can see that this is greater than 1, and so is this. And yeah, that's about it. Okay. All right, would you like to do one more or move on to a different type of problem?
Probably move on.
Sweet. All right, so let's go to the next page. There we go. Okay, so there's another type of problem we have here, and that is finding some exact values of some expressions. Whoops, not sine, but rather cosine. Cosine of 62 degrees minus sine of 28 degrees. Okay, so they want you to compute the value of this, get the exact value of it without using a calculator. Okay, so this can be kind of tough sometimes. There's some tricks that you can make your life a little easier though. So one thing that you can notice here is that, here, let's actually draw a diagram. So let's draw some form of right triangle. So sine and cosine are usually associated with right triangles, right? And that's because if you have some angle theta here, you can, if you know what this length is, maybe for right now, we'll just call it 1. Imagine it's a part of the unit circle. So this is a horribly drawn circle, but I think you know what's going on. So this is a part of the unit circle, and sine and cosine can be used to measure these lengths. So this would be cosine of theta. This would be sine of theta. Technically, if you have an arbitrary side length c, it's always going to be c times this. So that's kind of a nice rule with right triangles, is you can always compute the side lengths like that. But if it's just 1, then there's just a 1 times that. And so we can just get rid of the 1. But anyway, if we have some triangle, some right triangle, and this is 62 degrees, we can compute this angle right here. So we know the formula. It's the sum of all angles. So angle A plus B plus C, it's always 180, right? So if we know this angle, it's 62, and we know this angle, it's implicitly written as 90 degrees, then we can compute the last. So let's call this A, call this C, and this B. So now we want to solve for B. So B is going to be 180 degrees minus A minus C. So I'm just subtracting A and C from both sides. These cancel. This cancels with that. So we're just left with B on the left-hand side, just as we have here, and the 180 on the other side alongside the other two. Does that make sense so far?
Yes.
Okay, sweet. And now we can just plug in everything. We know what A and C are. A is equal to 62, C is equal to 90, B is equal to 180 degrees minus 62 minus 90. And I'm pretty sure if you punch this into a calculator, you'll end up getting precisely 28, which is the same thing here. So yeah, so let's go through that. We can just double check that's true. So it should be that 62 plus 90 plus 28 gets us back to where we were. This is 90, and for the rest of it to be 180, this plus this should be 90, I'm pretty sure. So then you have 90 plus 90, 180. So 62 plus 28 ends up giving us, let's see, that's 80, 90. There we go. So that's good. Sorry, I'm kind of skipping some steps, so you can double check that with the calculator, but trying to just go through some mental math, but regardless. So then we see that a triangle with this angle is also has 28 as this one here. Okay, so there's kind of a bizarre trick here But one thing you can notice is that if you were to look from this angle and imagine what cosine would be, cosine is going to be the adjacent over hypotenuse. So in our case, we kind of implicitly said that this is a 1. We can just define that so, just to make our life a bit easier. We're just kind of making up some things, but to illustrate the point, cosine here is going to be this length. Maybe I'll call this B, call this A, and this C I'll call 1. So then it's going to be cosine 62 degrees is going to be B over 1, which is just B. Now we're going to compute sine of 28 degrees. And now we look at this angle here, the opposite one, and we're going to look at the opposite side. So it's going to be this. It's the opposite over hypotenuse, which is B over 1, which is just B. So they're the same thing. They're both B. And if you subtract B from B, you get 0. And there we are. That's our answer. So that was a very overly complicated way of going about it, but that's kind of the intuition behind it, is you see that these values are exactly the same thing because they're both coming from the same triangle. You're looking at cosine of 62, so you're looking at the 62-degree angle, computing the cosine of that triangle from this perspective. And then you're looking at the opposite side of the triangle and looking at the opposite lengths. So we're both looking at the same thing, just different perspectives. And that's why they end up being the same thing. Sorry, I think I over-explained a bit much, but does that make sense? Am I illustrating that well?
Yeah.
Okay, sweet. All right, so yeah, that was kind of a tricky one, but it is a nice thing to keep in mind. In short, if you're on an exam, just try to see if 62 degrees, if this angle, if you subtract, oops, that was a horrible 90. If you can subtract 90 like so, and you end up getting the other angle, you can use this trick and they'll cancel out if there's a minus between them. But yeah, that's a trick you can keep in mind. Okay. Would you like to give, let's see, I have another problem here. It's kind of a same flavor. Would you like to give this one a try or no?
Yeah.
Okay. All right. So yeah, so in this last one, we're able to determine that this was very similar to this one. In fact, they are the same thing. So we can do a very similar thing here. So let's change this just a little bit. So we know that secant, using our identity, secant of theta is equal to 1 over cosine. Does that sound right?
Yes.
Okay, sweet. And then cosecant is the opposite. It's the sine. Okay, so let's use this. We can just replace this with this, and we'll do that as well. So this ends up being 1 over cosine of 55 degrees. Just replace theta with our 55. Cosecant, we can do the same thing, 1 over sine. Oops, not 55, 35. Whoops, my tablet's freaking out again. Why does it keep doing that? There's like some weird spot where that's happening. Okay, so from here, let's clean this up a little bit. What I'm going to do is I'm going to get rid of all of our fractions we have here. I'm just going to keep this main fraction here. So what I'm going to do is multiply by cosine of 55 degrees, and I'm going to divide by it as well. So these cancel out and just give us 1. So we're not actually changing anything, right? We're just changing how it looks. And also I'm going to do the same thing for sine 35 degrees. You can do these one at a time, but I'm just going to do both at once, just so it makes things a little easier. So all of these are being multiplied. Okay, so now we're going to see that cosine will cancel out with this. So we're multiplying divided by the same thing. We just get a 1. And now we just have a sine up top. And now we cancel this with this, and we have another 1. Therefore, this ends up becoming sine of 35 degrees over cosine 55 degrees. Okay, so we now made it a bit simpler, I think, in my opinion. It's this I feel is a bit nicer because, well, I have trouble remembering the secant and cosecant things, but I remember sine and cosine a bit better. So this, I would prefer to work with this, but it's completely up to you and whatever you're most comfortable with. So anyways, why did we do that? So now we can use the same trick we did before. So notice that if we take 35 and we subtract just like we did before, we'll end up getting 55 if I'm not mistaken. And we can use the same exact trick. Then that means this thing here is the same exact thing as this. So if they are the same exact value, then that means they cancel with each other and we just get 1. And there we are. There's our answer.
So the other time we got 0 and this time we got 1, what's the difference?
Yeah, so that's a good question. In this case, we're subtracting them. So we kind of have this value b, whatever this number is. We have b minus b. And regardless of whatever b is, it's they're still going to subtract from one another and you'll get 0 here. In this case, though, we have something like b over b. We don't really know what this value is per se, unless we want to punch it into a calculator, but we have the same value over the same value. So then that means they're going to cancel with one another and we just get a 1. So they're different operations.
Oh, okay, I get it now.
Okay, sweet. Yeah, so that's about it. If you want a shortcut in this problem, you can apply the same trick right here. But you have to ensure that they're kind of like the same thing. So sine and cosine, they're a very specific pair. They go together very well. Similarly, secant and cosecant are a pair. They go together very well. So you can use the same trick right here. So just 90 minus 55 equals 35. And that ends up being this right here. And because of that, then that means it's the same thing here. They both are equal. So this thing is equal to this thing here. And since they're equal, then we get this same thing right here, b over b, they cancel, give you 1. But yeah, sorry, I'm kind of over explaining, but does that make sense?
Yeah.
Okay, sweet. All right, so yeah, that's about that. Yeah, there is one more problem here. Maybe I'll just mention really briefly. It makes, the reason I'll bring it up is because it makes use of another identity that we know. So this is the last one. As in, normally this is pretty tough to compute, but one thing we can notice is, again, 90 degrees minus 40. I'm just choosing an arbitrary one of them. That ends up giving us 50, the other one. So what this actually means, I guess a better interpretation is that, or rather, I'll write it over here. That tells us that cosine of 40 degrees is equal to sine of 50 degrees. So, and vice versa. Sine of 50 degrees is equal to cosine of 40. Oops, did I? Oops, no, I didn't write that any differently. I mean, cosine of 50 degrees is equal to sine of 40. So that's actually what it means. That's kind of the intuition of why they're the same, is because they're both from the same triangle. But anyways, just going through this quickly, we can replace this cosine of 50 with a sine of 40. So we're lining up with this and it's equal to this. So then we can replace it. Sine squared of 50, or rather 40. And then we can use that one identity where we have cosine squared of theta plus sine squared of theta. And this gives us 1. And that's precisely what we have here. But yeah, sorry, I'm just kind of going through that quickly so that we can move on to other problems. But are you okay with that? Does that make sense?
Yeah.
Okay. Do let me know if I'm not illustrating well. We can go over it one more time. But yeah, okay, so that's about it. We can move on to the next. There we go. Okay, so now we have some slightly more complicated solving for triangle problems. Okay, so this is one. We have a right triangle still, but they're going to give us less information. Excuse me. And then we have an A, B, and a 10 there. And then this angle here is just going to be an A. And yeah, that's about it. Okay. All right, so they tell us to solve for everything in this triangle. So our goal, solve for A and lowercase b. Okay. All right, so perhaps we'll start with A. You have any idea how we can solve for A?
So 180 minus 20 minus 90.
Yeah, exactly. We're using that identity. 180 equals A plus 20 plus 90. Yeah, so that's where the 90 comes from. And what this translates to is A equals 100. Whoops. 180 degrees minus 20 degrees minus 90. Or simply stated, we can combine this and this. 90 degrees minus 20. And that just gives us 70. And then we know we have a 70 right there. And now we must solve for B. Oh, whoops, I also forgot. Oh yeah, that's right. We also had to solve for A. Completely forgot it. Okay, so we have to solve for now B and A. Have any idea some tools maybe we can use for that?
Maybe sine of A over little a equals sine of C over little c.
Yeah, perfect. Yeah, law of sines. Yeah, so sine of A over little a equals, and then you said C?
Yeah.
Sweet. Yeah, we can do that. So C in this case is just 10. So we can replace that there. Here, let me give it that. And we can also replace what we know for A and C, right? The uppercase ones. So we know that A is now 70 degrees. Oops. Again, I'm hitting that soft spot on my tablet. Oops. There. So 70 degrees. A, we don't know yet. C, we know is the angle C is 90 degrees. And then the side C is 10. All right, and now we have an equation with one unknown. We can solve for it. So we can, or perhaps I'll write it. We can multiply both sides by A, right? So then these cancel. And then we want to isolate A. So now I'll multiply both sides by 10. This will cancel with this. We have a 10 now on the left-hand side. And finally, we want to get rid of the sine of 90. But we can actually, we actually don't have to do anything. Do you happen to remember what sine of 90 degrees is?
No, I do not.
Yeah, I have trouble remembering it too. I think it says in the book in front of me, I think it's 1. So I think that's 1 right there. So then we don't actually have to divide it over because it's just 1 times A, which we can just ignore that. Just keep it as an A. So then now we look at everything on the left-hand side. It's 10 times sine of 70 degrees. Perfect. And there we can punch that into a calculator if we want. But maybe for right now, I'll just keep it like that until maybe if we need it or something like that. Okay, yeah, so that's perfect. So we use the, oops, gosh, I need to quit writing on the left of the tablet. So that was law of sines. Okay, so we got uppercase A, we got lowercase a. Any ideas on how we can solve for B?
Use a squared plus b squared equals c squared.
Perfect. Yeah, we can use the Pythagorean theorem. So yeah, a squared plus b squared equals c squared. So yeah, there's a couple other ways we can do it as well. We can also use law of sines, or even we may even be able to use law of cosines if we wanted, but both of those are pretty complicated. I feel that this is a bit more straightforward, so I would recommend this approach as you stated. But yeah, so let's just solve for b. B is going to be, get a to the other side. So we have c squared minus a squared. Take the square root. We can ignore the plus minus because it's just a length. And now we just plug in everything. C is equal to 10, and A we found was 10 times sine of 70 degrees. So we likely will need to punch that into a calculator. But for right now, we have 10 squared plus 10 sine of 70 degrees, whoops, degrees squared, just like that. Okay, so now we can punch this into a calculator. Here, let's see if I can.
In the above, you have c squared minus a squared. So is it subtraction or addition?
That'd be subtraction. And that's because we have to get a squared to the other side.
Oh, okay.
Okay. Yeah, so yeah. All right, so let's now figure out what a is. I think, here, let me pull up my calculator. So 10 times sine of 70 and then degrees. So it's just a little less than 10. I think it ends up being something like 9.4, something like that. So we have 9.4 squared plus 10 squared, which is 100. And then we have the square root over everything. So punch that in real quick. Square root of 100 plus 9.4 squared. All right, and I think that gives us our final answer to be, let's see, something seems a little strange about that. So B ended up being 13.72. Okay, something about that's oh, whoops. I think I messed up. Oh yeah, I think this may have been what you're referring to. This is supposed to be a minus. Sorry, I was like, yeah, that's a minus right there. My bad. Yeah, so I can kind of tell you my thought process on how I found out this was weird. So when going about an exam or something, if you see that one of the side lengths of your right triangle ends up being greater than your hypotenuse. So we found that C was less than B because this was 10 and this was like almost 14. If you see something like that, then there's something wrong. You can never have it that a side length of a right triangle exceeds your hypotenuse. So yeah, this was wrong. Oops. Yeah. Okay, let me clean this up a little bit. Get rid of that plus, minus, and then clean up that. So yeah, that should be something pretty small, I think. Yeah, it's about 3.4, if I'm not mistaken. Yeah, and I'm rounding. The problem may ask you to round to a certain decimal place. And just a reminder, this is the tenths, this is the hundredths, and then it goes on from there. Usually they'll either say tenths or hundreds or to like the fourth decimal place or something like that. But anyway, yeah. Does that seem okay? I likely will make mistakes, so yeah. Good to catch me when you can. All right, sweet. Okay, cool. So that was that problem. Would you like to do another right triangle problem like this, or would you rather do maybe some more obscure triangles that are maybe something not a right angle triangle?
One more right, and then we'll move on to the other ones.
Sounds good. All right, so let me move to the next page. All right, I'm probably going to avoid writing on the left because it seems as if my trackpad does not agree with that. Let's see, I'm trying to figure out where the issue is in my tablet. Seems to be fine now. That's strange. Anyway, so yeah, so the next triangle is like this. We have little a here, we have 2 on the side, 5 for the hypotenuse. We have an angle B, which is unknown, and then an angle A. So yeah, they don't give us a whole lot. They only give us one angle, the right angle. Okay, so yeah, our goal is to solve for little a, capital A, capital B. All right, so let's see if we can figure that out. What would you like to start with?
So we only have 2 sides and only one angle.
Yes, correct.
And maybe start by law of sines to figure out B.
Sure. Okay. Yeah, we can do that. So we can start with B, and then we have its opposite side, and then we have 5 or C. Or that should be lowercase c. Let me make it look a little smaller. Yeah, so we can use. I like to think of law of sines as like a. Perhaps I'll change colors. I like to think of it as like a diagonal. So if you have some form of diagonal like that, then you can use law of sines. So yeah, let's try it. Okay, so it'll be our known side of the triangle is going to be sine of c over lowercase c. And then the thing we want to solve for is sine of b over lowercase b. And this ends up providing sine of 90 degrees over c, which is 5. And then we have sine of b, which is our unknown, over lowercase b, which is 2. All right, so we can clean this up a little bit. This ends up just being 1 if we punch that into a calculator or try to remember the unit circle. And then we want to solve.
You just multiply by 2, right?
Yeah, exactly. So yeah, let's multiply by 2 to both sides. And we have 2/5 on the left-hand side, and then sine of b on the right-hand side. Okay, do you happen to know how we can solve for b?
Inverse.
Yeah, exactly. We do an inverse. So I'm just going to cancel that with that, and then we'll do sine inverse like that. Sine inverse of 2/5. So this is this I don't think is on the unit circle normally. This is something you'd have to just punch into a calculator. So let's see if we can figure that out. That would be sine inverse of 2/5. Okay, my calculator is telling me that that is about 23.6 degrees. So yeah, about that. Does that seem reasonable, you think?
Yeah.
Okay. All right, so we have that. And now using that, we can compute capital A, right?
Yeah.
So now we have, let's see, actually, I think we may have to be careful with this because it could be the chance that we have multiple triangles. Let's see. You remember how that one random rule where we could have two possible triangles coming from a sine inverse? So
Yeah, that's what what I haven't understood.
yeah, for sure. That's always the trickiest part. So the where it comes from is that I like to look at the unit circle. So the unit circle has that there's a couple different we have to look at where some trig functions are positive and where some are not. So the way I remember is all students take calculus. So all or A meaning all. So that means all trig functions, sine, cosine, and tangent. When I refer to all, I'm referring to all of these. And you can actually double check that this implies that all the other ones, the cosecant, cotangent, and etc., you'll be able to see that the other ones will also be positive. But anyway, this here means that all of them are positive in this first quadrant. In the second quadrant, it means that only sine is positive. Oops, so this is all, this is sine, and this is tangent, and this is cosine. Oops. So only those functions are positive. That's technically not true. You can also see that cosecant is also positive here, but this sine being positive implies that cosecant is positive. So yeah, just keep that in mind. So anyway, the reason why we have multiple values, or the potential to have multiple values, is because our sine function could spit out multiple values. So remember that the sine function represents how tall our triangle is. So if this is of length 1, we're on the unit circle, right? So imagine there's some circle going around of radius 1. Sine means how tall our triangle is. So in this case, it's going to be 2/5. But notice that another triangle on the unit circle right here can also have the same height. So perhaps I'll change colors. So this one right here can have the same height of 2/5, but it's a completely different triangle. So what does that mean for us? It means that this angle theta, I'll just call theta, and then this other angle here, maybe I'll call this theta 1, this one theta 2. They're completely different answers, but they both provide this. So that's kind of why there's two triangles on the unit circle that have a height of 2/5. So that's kind of where it comes from. Does that make sense? Or would you like further elaboration?
Yeah, like I get it that there are two, that there could be a height. Basically, I always kind of think of it like that, but a height of like 2/5. But the thing is, like, how do I know when to stop and what do I do afterwards?
Yeah, for sure. So yeah, one thing that you can do is first verify that this is a value less than 1. So sorry, I'm not getting to your question just yet, but I just want to mention this. In the actual procedure of doing this, you want to first double check that your answer, or not your answer, but the input 2/5 is less than 1. If it is, you can continue forward. So that's the first step. And then step 2 is when you have to account for two possible angles. Okay, so the first one is going to be this. So this is that theta 1. And now we have to consider, could there be a theta 2? So the way you would compute theta 2 is it's always going to be 180 minus the previous one you just found. So this is 20, whoops, the tablet's freaking out again. 23.6. So that's that one. So that is how you compute the other angle. We have not yet verified if this angle exists yet, but this is what it would be if it were to exist. Okay, so step 2, get theta 1. And then the next one would be and theta 2. Okay, now step 3 is theta 2 valid. So what this is actually saying is our triangle, this triangle over here, does it represent two distinct triangles? So that's what this question is referring to. Okay, so the question is, how do we check it? And the way we do that is by verifying that this is going, yeah, there's a formula for it. Let me see if I can recall. Okay, so we found out that, let's see, what angle are we given? We're given this angle right here, C. So we take the angle we have, that's going to be 90. So 90. And then we're going to add it together with this new angle, whatever this is. So I'm going to punch that into a calculator real quick. So that should be 180 minus 23.6 plus 156.4. Okay, so that's what it seems to be. That's what this is. All right, and we have to double check that this is strictly less than 180. That's the test. It's always the angle, if that's how you spell it, angle we know. In this case, it's the angle they provide us. In this case, C. And then we have 156.4. That is theta 2. If this is strictly less than 180, then this tells us, so if true, then there's two triangles. Okay, is that making sense so far?
Yes, it is.
Okay, great. Yeah, so let's actually double check if this is true. And it looks to me that this is not true. So this does not hold. So then that means, so if false, then only one triangle. And then we're basically going to throw away theta 2. Theta 2 does not matter then. If this is false, we don't have to worry about it. We only care about theta 1. And I think there will be some examples in the near future where we can actually see what would happen in this other case. But this is what we have currently, so we don't have to care about theta 2. Okay, so I think there actually is an easier way to go about this one, and I think maybe I'll briefly mention it. So this is the, I would say the, oh, tablet's freaking out. Oops. This is the general approach to solving triangles. So since we have a right triangle, we can actually make it faster. So if we want to solve, let's see, actually, is that true? Let me double check that we can do that. No matter what, we have to solve for one angle, or both angles. Sorry, just give me a moment to think about that and see if that's actually true. Actually, yeah, now that I think about it, I think we're forced to go about this way. And I think that's because we have the two angles missing. When you have two angles missing, that's when it's gets difficult. I don't think there's a quicker way to go about this now that I think about it. Okay, yeah, so that's about it. Any questions on that before continuing?
No, I'm good.
Okay, so just to summarize, we can solve for all the things we need. It gets a little difficult when you have two angles are unknown. If you have only one angle unknown, we can just use the 180 degrees minus 90 minus whatever, and then that'll allow us to compute the last angle. But since we have two of them missing, we don't know what this thing is right here, this blob. So then we can't use that. So what we do is we can use the law of sines. And if you're in a really dire situation, maybe you can use law of cosines. Cosines, it can be easier. Sometimes it's a bit harder. It's a harder formula for me to remember. So I think of it as a little harder, but regardless. So yeah, we go about this approach. And then when we come across a sine inverse or cosine inverse or something like that, we have to consider if we have two triangles or even no triangles at all. So case one, if this exceeds one, or it's less than -1, if it escapes the bound of sine, then we have no triangles. So I'll write it down right here. If that angle, I'll just say 2/5. 2/5 is less than -1, or 2/5 is greater. Whoops, no, this should be strictly not equal to. Strictly one of these, then there's no triangles. Then what we do is we continue forward. If it is between, as it is here, if it's between this, then we have either one or two triangles. So in that case, then we go through this. We check that it's in the bounds. It is. Then we figure out what θ1 and θ2 is. θ1, we just plug this into a calculator. θ2 is that's what we're doing right here, is we have this θ1 and we want to find the opposite θ2. So this is θ1, and this whole thing from here to here, it's 180 degrees. So we subtract them, and that's how we get θ2. It's or in other words, just the formula, 180 minus θ1. And this will give us θ2. So we compute both of those, and then we check if θ2 is valid. If θ2 is valid, or we go through that by checking this. And then, yeah, if it's valid, then we have two triangles. If it's not valid, we have only one, and throw away θ2. So that's kind of the summary of everything. It's quite a lot. Sorry, I know it's a bit confusing, but I hope that helped just a little bit. Okay, any questions about that? You want to cover anything over again?
No, I think I'm good.
Okay, sweet. All right, so let's do another one. Unless you'd like to move on to another topic, of course.
What was that?
Would you like to move on to a different topic or more solving triangles?
Just one more triangle and then we'll move on.
Sure. Okay, so we have been doing just right angle triangles. We are yet to do maybe more obscure ones. So I'll draw some triangle like this, just kind of drawing it arbitrarily. So we're told in this problem, we have A, B, C, little a, little c, little b. So we're told A is equal to 50 degrees, B is equal to 30 degrees, and A is equal to 1. All right. So 50 degrees, 30 degrees, and this is equal to 1. All right, so yeah, a little different than a right triangle. We can't use the Pythagorean theorem as we did before. Any ideas on how we can go about this one?
we can still solve C by 180 minus 50 minus 30, right?
Exactly. Yeah. Every triangle will always give you 180 degrees. So yeah, exactly. So 180, C is going to equal 180 degrees minus 50 minus 30. Okay, I think that's just 100, right? Does that seem correct?
Yeah.
Okay, sweet. So now we have C, and again, our goal here is to solve for C. Oops, C, and then little b and little c. Okay, so we have this one. We're good on C. Now we have to solve for A and B. All right, any ideas on how we can do that?
Law of sines.
Yeah, exactly. Yeah, so let's do law of sines. So the one we know is regarding C. We have both its actually no, the one
We know A.
yeah, exactly, is we know A. So it's going to be, oops, rewriting the same thing, sine of A over A. And then we can do, let's see, we can do either one. I think we can do either B or C. You have a preference?
No, I don't.
Okay. All right, I'll just choose B. And then we just plug in everything we know. Sine of 50 degrees over A, which is 1. And then sine of B is sine of 30. And then B is our unknown. All right, so just like before, we're just going to solve for B. This is actually just a 1, so we can kind of get rid of this whole divisor. And I'm going to multiply both sides by B. B sine of 50 degrees equals sine of 30 degrees. I'll get sine of 50 to both sides, or divide by it rather. These cancel. B is then equal to sine of 30 over sine of 50. Okay, so I'm just going to leave it just as it is in its exact form, rather than computing the decimal, if that's all right. And now we'll solve for C. Okay, so yeah, one thing I want to comment on is we could attempt to try to use the law of cosines rather than sine here to solve for this, but you'll see that there is a difficulty, and that's because we need 2 side lengths to do law of cosines. We need yeah, the formula, if I recall, is something like c squared equals a squared plus b squared minus 2ab minus cosine c. So we need 2 side lengths, a and b, to figure out the last c. And since we didn't have that, we could not have used it there. We could use it now if we wanted, but I think it's I don't know, it depends on your preference, but I think it's a little easier to use law of sines, but it's completely up to you. You could use it in this next one. Would you rather use law of sines again, or would you like to see what law of cosines looks like?
I like using law of sine.
Yeah, for sure. Yeah, me too. Okay, so let's give that a go. So then again, we use the thing we know, sine of A, which is just 50 over 1. Actually, just going to get rid of the, I'm going to get rid of the divisor bar because it's just a 1 underneath. So then we have sine of 50 over sine of, we're solving for C now. So the angle C is 100 over the length of C, which is our unknown. I'm going to get C to the other side. So then we have C times sine of 50 degrees, and then divide by sine of 50. C ends up being sine of 100 over sine of 50. And there we are. And we're done. Yeah, if your professor asks you to get a numerical answer, what you do is just punch this into a calculator and make sure your calculator is in degrees. Okay, any questions on that one?
No.
Okay, would you like to do We could do a harder one regarding if we have like two triangles. Would you like to do that?
Yeah.
Okay, sounds good. All right, let's go to the next page. Okay, I think this is one. Let's give this one a go. If it's not, then maybe we'll just do a different one, but pretty sure it is. So they tell us A is equal to 3, capital A is 10 degrees, and finally little b is 4. Okay, so just draw arbitrary triangle, A, B, C. All right, so A is equal to 3, capital A is 10 degrees, and then B is 4. All right, so let's see if we can figure this one out. Okay, so we have two unknown angles and one unknown side. Let's see. Would you like to do law of sines?
Yeah.
All right, so we have sine of 10 degrees over 3. So I'm using the A, and then perhaps I'll do the B because we know this side. So then that'll give us sine of B over 4. Just I like to bookkeep, so I'll just write B, C, and little c, just so I know what our actual goal is. So we're looking for capital B here. Okay, so just some more manipulation as we do earlier. So we have 4 sine of 10 degrees over 3 equals sine of B. And now we do the inverse just as before, right? So we get rid of the sine, put a sine inverse. Okay, all right, so let's go through our checklist. We first need to verify that this is less than 1, or its absolute value, for sine of 10 degrees over 3. And that's to make sure it is a valid input for our function. Because the output of sine only takes in values, or rather, yeah, the output of sine only gives us values between -1 and 1. So it's the opposite for the inverse. It only takes in values between -1 and 1. So for it to be valid, that has to be true. Okay, so let's figure out what this is. So sine inverse of 4 sine of 10 degrees over 3. Let's see. Actually, I think my calculator is having some issue. Oh, I think I know why. Let me put, oh, maybe not. Maybe I'll, sorry, my calculator is being a little weird here. Let me try something else to make it a bit, nope, still not working. Okay. Sorry, give me just one moment, having some technical difficulties. Okay, so what I'm going to do first is compute this. So this ends up being 0.2315 roughly. So I'll just maybe round it and say it's 0.2 just for simplicity, but we can guarantee that this is true. All right, so that's good. And now we need to compute sine inverse of 0. Oh, whoops, I think I may have, oh no, yes, that's correct. Okay. Sorry, I was thinking of something. Don't mind me. Okay, so now we just want to compute this. And now, let me punch that into my calculator. And I'm pretty sure this gives us, what is that, about 13.3 degrees? Yeah, that seems to be right. Okay, and that is B. There we are. So we found B, but now we have the potential to create a second one and have a completely different triangle. Okay, so we guaranteed by this that we know there is at least one triangle so far. So that there could be at least one triangle so far. Okay, so now we need to ask ourselves, is there two triangles? All right, so the way we do that is we compute the second possible value of b. So I'm going to call this b1. b2 is going to equal 180 minus b1. So we can punch that into a calculator. That is going to be 180 minus 13.3, which is 166.7. All right, so that's b2. So our check is that this is, so our check is that b2 plus our other angle, a. So we are given a, so that's why we're using this. We're going to check that this is strictly less than 180 degrees. And let's double check that. So that's 166.7 plus 10. Is that less than 180 degrees? I think that is. I believe it ends up giving us 176.7, which is correct, or a true statement rather. All right, so that's true. Then there's two triangles. Okay. Any questions so far? Do you feel okay with that?
Yeah, I'm with you.
Okay, sweet. All right, so now there's two triangles and they're going to be, I'll call this B1, and then I'll call the other one as a horrible triangle, but I think you know what's going on. So we have A, B2, and then I'm going to call this last one C2. So everything in this first one I'll call number 1, and everyone in this last one I'll call number 2. I'm going to keep A the same though, because A is the same in both triangles. And that was because they gave it to us at the very beginning. So, and to be a bit more precise, we actually use this to compute everything. So then that means it's a part of it. Okay, so this is now our triangles. Actually, I think I'm gonna put this down just a little bit so it's a bit easier to read. Okay, so this is A, B2, C2. And we still have A equal to 3 because they gave it to us, B is equal to 4. And now we have little c1 and little c2. Okay, so B1 in this one triangle was 13.3. That's B1. And B2 is 166.7. Okay, so that's everything we know so far. All right, so let's start with the first triangle. We'll start with solving everything there, and then we'll solve everything here in the second triangle. Okay, so how do you think we can solve for C1?
So it would be 180 minus 10 minus 13.
Perfect. Yeah, that's exactly right. So we can just solve for it in that manner. So that's going to be 180 minus 10 minus 13.3. All right, so let's compute that. 80 minus 10 minus 13.3. There's 156 with a decimal. 156.7. Okay, so that's C1. Perhaps I'll change colors just to make things a bit more distinguished. Okay, and now we just have to solve for little c in the first triangle. Okay, you have any preferred method?
What are we solving for? Little c?
Yeah, exactly. Yeah.
So law of sines.
Yeah, sure. So maybe I'll do that in blue writing at the bottom. So it's going to be sine of what we know. So maybe I'll use A, 10 degrees over 3 is equal to sine of C, which is 156.7 degrees, all over C1. Whoops, let me make that a little c. There we go. It's not much better, but whatever. So then this provides us C1. I'm just kind of skipping some calculations. So that should give us 3 sine of 156.7 over sine of 10 degrees. Yeah, feel free to double check me. I'm pretty sure that's correct if you just kind of get everything over to the other side. But yeah, so then we can just punch that into a calculator, and then that will be our answer for little c right here. Okay, so now moving on to the next triangle, we can do the same exact thing, but for the other two. So this one is going to be 180 minus 10 degrees minus 166.7. And yeah, perhaps I'll just leave it right there for time. You can just punch this into a calculator, and I'm pretty sure you'll get quite a small answer. I think you'll get something like 3.3. I'll put a question mark right there because I'm not entirely sure, but I think you'll get something like that, a very small angle. And then for C2 here, you can repeat the same exact process, but with our new numbers. So that'll end up being, that'll give us sine of 10 over 3. I'm using this and this, which is sine of 3.3. I'll put a question mark again. It'll be something like that, and then C2.
I checked, it is.
Okay, sweet, awesome. I just kind of guessed by looking at this result we figured out earlier. Just kind of seemed like it'd be 3.3 or something like that. Yeah, okay, so now we get C2 to the other side, and we'll end up getting something very similar to the last one, but it'll be 3 times sine of 3.3 degrees over sine of 10. And you'll end up seeing that the only difference between this and this is what we put in for this angle and this angle. And that's because C, the angle C is different in both. And that's really the only difference between these for this calculation. And there ends up being our answer. And yeah, that's about it.
Okay.
So that's what happens when you have two triangles, and yeah, it's just double the work really. But yeah, again, the reason why this happens is because we have a lack of information. We don't have as much information as we want for our triangle. So it ends up giving us the possibility of describing two different triangles. If we had a bit more information, like for instance, if they gave us all the lengths of the sides, I'm pretty sure you'll see that that won't happen there, but maybe I'm wrong. Maybe I'm forgetting something. But in certain cases, like we saw earlier, we have enough information, so then we'll end up being able to solve everything we need. But yeah, that's about it. Okay. Any last questions on how we went about that?
No.
Okay, sweet. All right. So there's a few more types of problems. I think there is some word problems, and I think there's also finding area of triangles. Do you have a preference?
Yeah, they're both of them. So which one was, so it's area of a triangle, and which one's the other one?
Just some word problems. I don't think there's anything specific regarding word problems, but I think it's just more solving for triangles, but they throw this whole real life application at you, and you got to try to figure out what's relevant, what isn't.
Oh, okay. So let's just do a word problem then.
Okay. All right. So let's see if I can find a good one. Let's see. Okay, let's give this one a try. See if it ends up being somewhat reasonable. Okay, so I don't think I'm trying to think of how I can share this on the screen. Perhaps I'll just say, they give us some drawing here. So they give us this, and there's some boat right here. I'll just draw a box for simplicity. And then they tell us that this is 5 degrees. And they tell us that this length here is 1,454, and that's in feet. And then they have some city, so some city over here, and it goes for about 1 mile. And then they have some sea all the way up into the boat. Okay. All right, so that's what they give us this illustration. They give us a written description. They say that there's a tower. There's a tower like right here, and this is the height of it. And it is, it says it's situated about 1 mile inland from the shore of Lake Michigan. So we can presume that that's the lake. And then it says an observer in some form of our boat on the lake directly in front of the tower looks at the top of the tower and measures the angle of elevation. So this person sitting on the boat measures this angle of 5 degrees. And then they want us to figure out how far offshore is the boat. Okay, so let me write that. So our question is, how far offshore is the boat? Sorry, I keep moving the window around. Okay, so that's the question, and we have to try to figure out how that is, how that translates to our diagram. Okay, all right, so one thing we can do is yeah, so we have to figure out precisely what it is we're solving for, and I'm pretty sure we're solving for this distance right here. Does that seem reasonable to you?
Yes.
Yeah, okay, so that's what we're looking for. So the question is, how can we find that given the information we have? Okay, so this is a right triangle. At least we can assume it to be. We can assume that the land is level right here, and that this forms a right triangle. Okay, well, I think what we could do is try to solve for this entire length here. So maybe I'll call this A. And then maybe I'll call this B, and I'll call this C. Okay, so perhaps we could solve for A. Put a question mark right there. Maybe that's something we want to do. Okay, so we don't know anything about C. Yeah, not yet. I don't think they'll give us any other information. And yeah, they don't tell us how long C is. We just know this. Okay, so what other information we know? We have this here. All right, is there any way we could try to solve for C? Do you have any ideas how we can do that?
Not really, because I would say we could use law of sine since B is 145 and B, the degree is 5, but yeah, I don't know about that.
Yeah, so one thing I'm kind of thinking is how we went about those last problems is perhaps we could use law of sines. So we could use the fact that since this is a right triangle, kind of thinks that maybe we could solve for A using law of sines. or see law of sines and then compute that a different way. So that's one way of going about it. Perhaps an easier way is just to solve for a directly. So let me change colors real quick. So we can use law of sines using this and this. What do you think about that?
Yeah.
Okay, so we can do that, and that would require us to solve for capital A. But we can do that, right? We can just solve for it using the other two angles. So that'd be 180 degrees minus 90 minus 5 degrees. So I think that would be what, 85, if I'm not mistaken. And then from there, we can use law of sines. So then sine of perhaps I'll do B. So 5 degrees, that's the thing we know. And that's over 104, 1,454. And then we have that is equal to sine of 85 degrees over little a, right? Okay, and now we just solve for a. So I'm going to manipulate this expression a bit. So we have a equal to, pretty sure this will end up being 1454 sine of 85 degrees all over sine of 5 degrees. So you can double check me on that, but I think that's right. And that will be our answer for this entire side. So how do you think we could solve for this length then?
Subtracting it?
Yeah, exactly. We can subtract the two. So maybe if I call this x or something, x is going to be 1 mile minus whatever a is. So sadly, these have different units. This is in feet, and this is in miles. So we have to figure out how many feet are in a mile. I can never remember off the top of my head, but using that, convert this to feet. So go miles to feet, and then we could subtract them, and then that'll give us our answer for x. Okay. Do you feel okay with that? You have any questions?
Yes, I'm okay with that.
Okay, sweet. All right, so we have a little under 10 minutes. We may be able to do another problem. Would you like to do another? I could try to do another word problem, or we can do some area problems. What would you like to do?
Let's do an area problem.
Okay, sounds good. All right, so they give us some triangles similar to before. So they give us a equals 50 degrees, b is equal to 30 degrees, and then they say a is equal to 1. They say find the area of the triangle. Oops, I keep dragging the window. Okay. Okay, so let's depict our triangle. A, B, C. And then this is little a, this is little b, and this is little c. Okay, so now we fill in everything. 50 degrees, 30 degrees, and a is equal to 1. All right, so there's a couple different formulas for this. I'm not sure which ones you have seen, but I can list out a couple real quick. So I think they use K in the book to distinguish from this A. Normally A is used for area, but K is also sometimes used.
Yeah, I can give it to you. So she first, oh, well, this is different because she gave us two formulas actually, one for side angle side and one for side side side.
Yeah,
but
for
this
sure.
is two angles and one side. Well, she didn't give me that one.
Okay, so yeah, there's a couple of them. There's 1/2 base times height. That's 1. So this is base. I think this is kind of like the classic formula. I don't know if you can say a quote unquote classic one. And then there's another one, which is 1/2 AB sine of C. And this one is, so A and B are just these A and Bs, and you can swap them out for any other angle if you want. So, or rather any side. So it's just any two sides and then the opposite, the other angle. That's how this formula works. And then finally, the last one, I would say the more notorious one is S minus A, S minus B, S minus C, all under the square root, where S is equal to 1/2 A plus B plus C. I think this is, I forget what formula this is. I think it's like Huron's formula or something like that. Maybe I'm.
Yeah, that one's the one she gave us.
Oh, okay, sweet.
The last one.
Yeah, so this one requires all three sides, and sadly we don't have it. We have only one. So maybe it'd be better for us to maybe use the second formula or something like that. Here, let's see if we can do that. So this would require two sides. We have only one side. Okay, so is there any easy way we could try to find another side? Is there any ideas on how maybe you'd find another side?
Maybe we can find little b by using sine of A over A and sine of B over B.
Yeah, sure, that sounds good. Yeah, so sine of 50 degrees over 1. So since that's just 1, actually, I'll just erase it. And then we have sine of B, 30 degrees over little b. So that ends up giving us b equal to sine of 30 degrees over sine of 50 degrees. There we are. So that wasn't too bad. We're able to figure out the other side length. And now we need C. So then C, we can capital C. So we can just do that how we did before, right? C is going to be equal to 180 degrees minus 50 minus 30, which is just 100 if I can subtract. And yeah, so now we can just punch in everything. So K is equal to 1/2. Maybe it'd be easier to punch this into a calculator first, but regardless, it would work by just, yeah, you just punch that in, and then, so then we'd have something like sine of, and then we'd have sine of 100 degrees. And we just punch that whole thing into a calculator. And that'd be about it. I think this gives us, something like 0.32 as our answer. And that would be in square units, or yeah. If they wanted some form of unit, it'd be something like that. But I would say just this is fine. Okay, any questions on that?
No, no questions.
Great. So yeah, that we have about 2 minutes. So yeah, I think I'll close up the review. And
Yeah, thank you.
yeah, of course. I hope this was a little helpful. And yeah, I hope your exam goes well. One thing I usually like to do, and maybe you'd find it helpful, is there's exams like these require like a good amount of memorization sometimes, like law of sines, law of cosines, all the area formulas, and it's sometimes difficult to figure out which one you need. So usually what I like to do is I see a lot of people like studying a lot before an exam, but what I do is I'll study a lot and then I'll just kind of stop like an hour or half hour before, just kind of accept what I know, because I know a lot of the time I'll second guess myself. Maybe that would be helpful, but yeah, that's about it.
Okay, thank you.
Yeah, have a good one.
Thanks, you too. Goodbye.
Bye.